Hi, my name is Bryce Newton, and this is homework 9, problem 6.23. And we are given this schematic of this RLC circuit, and we are asked to find this transfer function of the voltage out over the current in. And they specifically ask us to use the impedance method, which is convenient because it can allow us to model this like resistors. And as you can see here in this circuit, these are in a parallel alignment. And so as I was recalling how to combine these equations here came to mind, and these will be very helpful here shortly as we combine these, this resistor, this capacitor, and this inductor. So first thing you need to realize is that this is in a parallel alignment. And with that being said, you can model this like this diagram I've shown here. We will add these together, but in order to do so, we need to follow this equation that is for the parallel diagram. And so as we take the inverse of the resistor and then inverse of the inductor, we'll just take the normally the capacitor is inversed, but the inverse of inverse obviously is just the regular form. And so when we have that as our total capacitance, we can then plug that into the Ohm's law equation, where we have the voltage, current, and as we're treating all these together as our impedance or as the total resistance, we then can gain this particular expression. As I was saying, basically you need to put the resistor, and since we're kind of classifying these all as a resistor, so to speak, with the impedance method, we can then gain this equation. And one thing to note is this inverse, this -1 here, because this would, without the -1, this total resistance is 1 over the total impedance. So by taking the inverse, you're putting it back into, let's say, a whole number as opposed to a fraction. So when combining these, obviously the denominators need to be alike. So as we multiply through these 2 by R, and then the resistor and the capacitor by the inductor, we get like terms in the denominator, which then we can combine all the elements in the numerator, which conveniently can be inversed. And when we, if you remember, the original question was to get the transfer function V over IS just simply by dividing by the current and taking the inverse of our impedance, we get our final expression for our transfer function here. Hopefully this helps you, and thanks for watching.